Lesson 14 is vectors in 2 dimensions, which is quite a bit more difficult than vectors in 1 dimension. Let's just quickly review what we mean so you know the difference. So anytime you're talking about vectors in 1 dimension, they are going along the same line. They can be going in different directions along the same line, but it's along one line. So these are examples of vectors in 1 dimension. So those are all along the same line, and you can add those. For example, that blue one, I can just take the blue one, this here, and put it tip to tail, and then the resultant is tail, tail, tip, tip. Okay, so those are all on the same line. They can be left, right, up, down, diagonally, as long as they're on the same line. Vectors in 2 dimensions means that they're not along the same line. So for example, one vector may go to the right and one vector may go up. Right, so that's in 2 dimensions, an x and a y component. And that's the kind of the theme of this lesson is components. So if I draw a vector, I can separate it into an x and y component. Now let's go over this preliminary stuff first. So you need to know SOHCAHTOA from trigonometry, grade 10 math, and you need to know Pythagorean theorem, which you learned in junior high. And if you know those, then you're good to go on these. So what we're going to do, let's have a look at the examples here. Components of vectors. Just like a component stereo system is made up of several individual working parts, components of vectors are individual parts that add up to the overall resultant. So this time, you've got a car that drives 10 kilometers east and then 7 kilometers north. Determine its displacement. Okay. So here we go, 10 kilometers east. And I can't even remember, 7 kilometers north. So we can place these tip to tail right away. There's our 10 kilometers east. Now let's just go 7 kilometers north. Tip to tail. And just like one-dimensional vectors, the resultant vector goes tail, tail, tip, tip. Tail, tail. Tail, tail. And up here, tip, tip. And that seems pretty intuitive. If I go 10 kilometers to the east and then 7 kilometers to the north, I've gone in a general northeast direction. I say general because if you say northeast, that means exactly northeast. It means exactly halfway between north and east. So I'm going in a general northeast direction, and that's my vector diagram for this. And as you can see, when you draw these vector diagrams, you're creating right-angled triangles. And therefore, you can solve this triangle using Pythagorean theorem and SOHCAHTOA. Okay, so let's do that. I know the whole rest of the lesson kind of goes through this, but let's just solve it right here because it's pretty straightforward. We're going to call that R. R stands for resultant. Usually in Pythagorean theorem, you probably call that C. A squared plus B squared equals C squared. We're just going to call it R for the resultant vector. And then we're just going to say R squared equals 10 squared plus 7 squared. That's simple Pythagorean theorem. Solve for R. Remember, you've got to take the square root, so it's got to be so R turns out to be 12.2, which makes sense. Clearly, it's not 149. If this vector here is 10 and this vector here is 7, there's no way that that purple vector can be 149. 12.2 sounds reasonable. It's the hypotenuse. It's going to be longer than the other two sides. And then we have to find the angle, because now we want the displacement, not the distance. So this person has gone 12.2 kilometers, but since it says displacement, we also need the direction. And the direction is we're going to find an angle, and it is always the angle between the two tails. So this angle. And that little symbol there is called theta. We typically, finding an angle, we designate as theta, just like you would designate something as x. We designate this as the Greek letter theta. And you can see, I could use any trigonometric ratio to solve for theta. I'm going to use tangent. The reason I'm going to use tangent is because 7 and 10 were given to me. And in regards to angle theta, 7 is the opposite, 10 is the adjacent. And so to solve for the angle, I'm going to go tangent theta equals the opposite over the adjacent. And then I have to use my inverse tangent feature on my calculator. And that's going to give me an angle of 35 degrees. Okay, so pretty straightforward so far. We've got the result, the length of the resultant vector, 12.2. We've got the angle. The difficult part here is, how do I express that angle? I can't just say 35 degrees because I need to give it in terms of direction. So I went east and then north. And this is the way we're going to do it. There's 3 ways that you can do it. 2 of them are the only ones you really need to know. Oopsie. And this is my preferred way. The preferred way of expressing that direction is to look at the triangle, and you can see that we're starting at east, and we're going towards the north. So if you're just watching the mouse here, we're starting at the east, and then we're going towards the north. So I'm going to say east 35 degrees north. That's in my opinion, the best way to express that angle. You could also say 35 degrees north of east. That is totally acceptable. The reason I don't like that one as much is because it uses an English word, and we want to be as universal as possible. And so we avoid using a word in a specific language. Now, of course, north, south, east, west, they're also English words, but those are probably more universal. So, or you could say 35 degrees north of east. And then you have to express the answer as a whole. And so the whole answer for this question, it was asking to determine this displacement. The answer is 12.2 kilometers east, 35 degrees north. And that is essentially, that's a whole lesson we've just done in that one example there. Let's just go and look at the rest of the lesson. Where is the rest of the lesson? Okay, apparently there is no rest of the lesson. I'll have to do that in a separate video, but you've got the basics right there, and then we'll do a part 2 for the rest of the lesson, which seems to have disappeared. Tragic.